This course is about design verification and test of digital VLSI design. Basically, we are having three components in this particular course. One is design issues of your digital system, second one is verification, and third part is your testing of our design. In our last part, in the first part already we have seen what are the design issues involved when we are going to design a digital system. In second part it is the verification, and third part is testing of our product. So, in this verification part, what basically we are going to do, what need to be verified and why we go for verification. Without verification, whether we can design our circuit, we can develop our circuit or not, we are going to look all those issues. So, in this particular part, we are going to look for the verification issues, and one of the component is using a logic for verification. But before going for that particular logic, basically we are going to cover about temporal logic. But before going for temporal logic, we want to see what are the methods used for your verification and why it is needed. It is basically some sort of introduction I am going to give, and I will say why it is needed, why we should go for verification. So, if you look into it, in our design cycle, basically we are going to get those following steps: specification, design, implementation, testing, installation, marketing and maintenance. So, in our first part, basically we are talking about this particular design issues, and when we go for design, we need to know the specification of the system. That means, as a designer, we are going to design a device, and for that we are having some intention. That means, my design should satisfy some specification. First of all, we have to give this particular specification. Just give a brief idea what we are going to do in specification and where from that specification will come. Just we will give an example. So, you just said it, we are going to design a controller for our washing machine. What we can say about washing machine? We said that our design or our controller of washing machine should satisfy some property, and this property or specification can be mentioned as the dryer is activated after the wash, not before. So, because first we are going to wash the cloth, after that we will activate the dryer to dry our cloth. Second, maybe we can give one specification something like that: water is poured in before the detergent and it is drained before activating the dryer. So, these are basically our requirement, or we can say that these are the property that my controller should satisfy. And another specification, we can say that cold water is to be used for your soft wash, because if we are having some soft wash, or sometimes we need to use hot water for our heavy wash. So, accordingly at appropriate time we have to activate our heater. So, these are the several components that we have, and according to our requirement we have to activate those particular component. Now, this is about your specification, design, and one design is completed, then we will go for the next phase is our implementation. We are going to implement our controller. After controller is implemented, then we need to test it whether we are getting a correct result or not. But you just see that here we are having this particular testing, and when we are doing it, this testing we have done after implementation. That means, after completion of this particular three phases. So, that means we are going to test about the correctness of our product. Then it will come for the installation and then maintenance. First we have to install, or maybe we market the product, and once it goes to the market, then what will happen? We need to have the maintenance phase. We have to maintain it. So, here we have one issue that whenever we are going to design a circuit or going to design a system, it may not be correct in the very first go. So, it says that bugs reported at the early phase of design incur less cost for debugging. So, when we are coming to this particular testing phase, we are testing it, and how we basically test, we know our input pattern, what are the inputs that we have to give. Along with that, we know what are the desired behavior. So, basically we can say that my design, I can say that I am designing a device, this is my device, I can treat these things as a black box. Now, there are several inputs are available for this particular device, and according to this particular input behavior, we are going to get some output. No, we know the output behavior of this device according to this particular input combination, what are the input combination we have. So, during testing we are going to test for those particular input pattern and we see whether we are getting the desired output or not. So, in this particular case during testing we are looking for both testing, actually two types of testing, one is your functional testing, second one is your manufacturing default, because during fabrication, during manufacturing some fault may come into picture due to the faulty manufacturing. So, in testing we are going to capture those particular issues also, and if device is really faulty, then we have to discard it. But if it is having some functional error, then what will happen? We have to go back to our specification, we have to revisit our specification, we have to look for our design issues, then we are going to redesign it or we will revisit our design. Once we fix the bug, basically it is we are going back over there due to some bugs that has been reported. So, due to those bugs we are going to fix it and eventually again we follow this particular part, we may have to do several times. So, it says that since after implementation we are testing it and we can capture the bugs at that particular point only after test. So, we are going a long way to get our test. So, it says that if we can capture the device fault, your design fault in this particular early phase, then what will happen? It may reduce our cost, because again another factor we are having time to market also. In some specific time we have to release our product to the market. So, that is why we are thinking whether this particular test or thing can be done prior to this coming to the implementation or not. So, for that in our design cycle we are incorporating one more phase over here, which is we are talking about that verification. And in this particular part of our course we are going to look for those particular verification issues. What are the ways that we are going to verify, what we are going to verify, and up to some extent I will say why verification is needed. And secondly, there are several ways of doing the verification, but here we are going to look for formal verification only. So, here what we can say that verification is used to capture the bugs at the early phase of design. You just see that we have placed the component verification just after design. By looking into our specification, we have come up with a design, and after the design we know that for a specific purpose we are going to design a device. That device should satisfy some of the property or some of the specification. In this verification phase we are going to check for this particular correctness of those property, and we can say that this is some sort of your property verification, or we can say this is a functional verification. We are going to verify the functional property of our device. Once we satisfy that our whatever design we are doing, it is going to satisfy our requirement, then we will go for implementation, and after implementation we will go for testing. So, when we are coming to this particular testing point, then basically it is remaining left with your manufacturing defect only. So, we are trying to capture most of the design issues or design bugs in this particular verification phase. Now, we are talking about here that verification. Now, what are the different ways that we can do it, whether it was there or not in the earlier phase. So, in most of the cases we are having that particular notion of having simulation. We do the simulation of our entire device and we check whether our design is correct or not. So, basically in simulation what happens? Again we think that this is my device, I have designed it, and we know that this device is having several inputs, and we know depending on the input pattern we should get desired output. So, we are going to check those particular desired output with respect to this input pattern. So, this is a basic simulation. So, we are going to have a simulation model of our device and we are going to check it, and if we find that it is correct, then we go for fabrication. But whether is it possible to go for simulation for all type of devices? If you look into that issue, you will find that now the system or devices are becoming more and more complex, and we are having complex design for the devices, because now due to the advancement of our semiconductor technology, you can put more and more component in a silicon wafer. So, we can go for a complex design, and depending on our design, the number of input is also increasing. So, the number of possible input cases, maybe you can say it is your 2 to the power n if we are having n number of input signals. Okay. So, it is exponentially growing. So, for that it is not possible to simulate for all possible combinations. So, people are saying that we are going for a selective simulation. So, that is why it is talking about this non-exhaustive simulation. In case of exhaustive simulation, we try to test it for all possible combination, but due to the large number of input combination, because the input pattern is your exponential in the number of input signal, it is not possible to test the entire circuit for all the possible combinations. So, for that we go for selective simulation, and we say this is non-exhaustive simulation. So, what we said that number of test cases are exponential, already I have mentioned. So, in that particular case we are going to test it for some fixed number of input combination. So, here instead of going for your all possible combination, we will go for some selected combination. So, just I am summarizing it. To find the appropriate subset, it is again a complex problem. So, we are having another research problem over here, how to find out the appropriate subset of those particular input pattern. This is come under this particular test case generation. Okay. Since this is another domain, we are not going to look into these issues over here, but just I am mentioning that this is another program, or we can say that ATPG, automatic test pattern generation. With the help of those particular techniques, we can find out what is the appropriate subset to test our design. So, since we are going for non-exhaustive simulation, so what happens? We may not cover all possible error cases. It is quite obvious, because it may happen that some of the combination may not be captured by the test cases that we have given. Now, from exhaustive simulation we are coming to non-exhaustive simulation. So, in this case you just see that what may be the problems that we may face. You just think we are not considering all possible input cases, and we are giving a subset of it. Whether that particular subset is capturing all possible error combination, it is already I have mentioned that it is another problem, another complex problem. It is difficult to find it out, but still we are having some heuristic. With those particular heuristics, we try to get a reasonably good or sound set of test cases. So, people are working with it, it is going fine, but what problems are coming over here? Why we need to go from your non-exhaustive simulation to some other domain? In this class, I am going to cover about your formal verification. Why we need to go for the formal verification? Necessarily, we have some problems in non-exhaustive simulation, and it is quite obvious. You just see that we are not considering all possible cases. Now, you just see, now we are going to see what is the problem. There is a Pentium bug. I think you might have heard this particular term, what is Pentium bug, and this is a major challenges that Intel has received in early 90s. So, what happens? Intel has released their first Pentium series of their product in 1993. So, you know say that Intel is a big house is your processor design, and if you look into their history line or timeline, you will find that they have started with Intel 8086 as the basics processor, then they have go with 186, 286, 386 and up to 486. They have gone, and you know that this is your upward compatibility. Upward compatibility means whatever we can do in 186, same thing can be done in 286, but with enhanced features. So, this is their timeline. So, after 486, they have released the product Pentium series. Again it is upward compatible, whatever we can do in 486, same thing can be done in your 586 or that Pentium series. Now, say it is upward compatible, whatever we are doing in 486, same thing can be done in your 586. But where from this bug is coming? You just see that a year later, an estimated 2 million had been sold. It was discovered that there was a flaw in the hardware of floating point division. You just see what is happening basically. So, they have released the Pentium, it is upward compatible, whatever we can do with 486, same thing can be done in Pentium. Along with that, we have some other additional features. The Intel design team has designed it properly, and they have tested it, and they have released the product. But after 1 year error has been reported for division only, floating point division, which was there in 486 also. So, where from this particular error has occurred? Now, you see that in their timeline or during the design they have changed their division algorithm. So, earlier they have used some other algorithm, but in Pentium series they are looking for a faster algorithm and they have used this particular assertive floating point division algorithm. This is basically assert is coming from 3 scientists named Swaney, Robertson and Tosser. They have devised this particular division algorithm. Since it is a faster algorithm, so Intel has decided to use this particular division algorithm in their new Pentium processor. So, what is the difference? So, basically what happens in this assertive division, we have to use a lookup table to find out some input pattern looking into some input combination. So, they have implemented this lookup table in their RAM, and due to an error in this particular one entry in this particular lookup table, for some input combination it is giving error. So, this was the problem basically, this is the Pentium bug. So, we are having a lookup table, we had some entries in the lookup table, but there is an error in one entry, and whenever we are going to use that particular entry, it is giving us a wrong result. But see, Intel people have tested it. How they have tested it? They have gone for non-exhaustive simulation. Okay. So, with non-exhaustive simulation already I have mentioned that it is not possible to capture all error, because we are very much selective about our input test pattern. So, some design flaw or error may slip over. So, this is the case where this particular design error has slipped. So, for that, after this particular Pentium bug, so it is Intel is a big business house, so they can sustain such type of loss, because what will happen, since about 2 million chips they have released faulty, what they did, they call back all those particular chips and replace it by a new one, and for that they have incurred a loss of $500 million. Since Intel is a big house, they can cope up with this particular error. So, from this particular error, all EDA companies has learned a lesson, and they found that, or they think that non-exhaustive simulation is not the solution. We are coming from exhaustive simulation to non-exhaustive simulation, but that non-exhaustive simulation is not the right one to do. It is not going to give an error-free design. At that point, people are thinking of what to do. So, in that case, this notion of formal verification is coming into picture. Is it not like that? We are encountering this formal verification after Pentium bug. It was there. Researchers are working with this particular method for how to formally capture the design, how to formally specify our property, and how to check that the specification or the property are true in this particular design. So, this is basically formally we are trying to capture everything. It was there, researchers were working over there, but industry people are slightly reluctant to use it. But after Pentium bug, all people has think about it. Now, we should look for the alternative. So, people are going for this particular formal verification, and what are the issues that we can address over here. Already I have said that it is the design complexity is increasing day by day, because in a small silicon area now we can put more and more components, and indirectly it means that we can place more and more devices in same or small silicon area. That means, we can place a complex circuit or complex device in a small silicon area. That is why the complexity of the design is increasing. So, what we do in formal verification, basically we start from our abstract model. So, we know our design, we know our objective, but instead of going to the direct product or direct design, what happens, we try to abstract out the relevant information, and we are coming up with an abstract model, and generally we deal with this particular abstract model. So, how to come up with an abstract model? For that we need formal methods, we use some formal methods, formal mechanism, and after that we apply some verification techniques, and that is why we generally say this is the formal verification. So, model help us to build more complex system. Already I have mentioned that whatever is relevant, whatever is required, we try to abstract it out, we have a design out of it. So, some sort of modular design case we can think about it, and for every cases we can have a small model with try to capture the design behaviors and we know what are the property or what are the specification which is satisfied, we are going to look for the satisfaction of those particular property. So, again on the other hand, a model is easier to understand than a whole system, because we are coming down to a smaller piece of a whole system. So, in this particular case, we are going to construct a model in which we can demonstrate a certain property holds. So, we need two things, one is your system model and second one is your specification of the property. You just see that already I said that I am going to look for a model, somehow we are going to give our design and we said that this is our model. Another one, we are going to have the specification or the property. We know that I am going to design a new device and that device should satisfy some of the property. Already one example I have given, that you are going to design a controller for your washing machine and you said that it needs to satisfy some of the property. Secondly, if you look into the formal verification of formal methods, it is not like that we can apply only in your designing of VLSI circuit or hardware circuit. It can be applicable in any design. Okay, one simple example I can give. Say you are working in say network, in computer network and you are designing some new computer protocols, that transport protocol. Now, in most of the protocol, what will happen when you send a package or message from source to destination, what happens generally, that source expect that it should get back the acknowledgement, then only the sender will be knowing that that message has been delivered properly in to the destination. So, what is my requirement over here? I can say that when sender sends a message, eventually it should get back the acknowledgement. So, this is, you can say that this is the property or this is the specification of the protocol that I am going to design. So, I am telling you what is the specification, but somehow formally we can specify or we have to capture this particular property. Similarly, that about your system model that we have, that also formally we have to devise, we have to design and eventually we are going to check whether this property is satisfied by this particular model or not. This is the formalism or the formal mechanism and we said this is the formal verification. So, again now already we had the testing and now we are coming into formal verification. Now, what is the difference between those two things? So, what is the testing and what is the verification? Basically, in testing we talk about what is wrong. So, this is basically testing. So, we have the device, we have the product, we test it and we said that this is the testing result, it says what are wrong in that particular case. But in case of your verification or when we are going to do it formally, then we can just try to address this particular issue, why it is wrong. So, just say that after your design phase, we will do the verification and in verification, we will give the feedback why something is going wrong, why it is wrong. So, when design team gets this particular feedback, then what they can do, they can revisit their design, they can fix up the bug, they can fix up the error and they can rectify their design and come up with the new rectified design. So, with this new rectified design, again we apply this particular verification and when we are satisfied that okay, now it is satisfying all my properties or all my requirement, then we proceed further, then we will go to the next phase. Basically, next phase is implementation or fabrication. So, how we are going to do this formal verification? So, there are several approaches to go for verification or defining the system formally and specifying our properties and looking for the correctness of those properties in our design. Since there are several mechanisms, several approaches are there, but in our course, in this particular course, we are going to look for the logical formalism. We will see how the logic is used for our formal verification. We may not go for the other issues. So, if you look into this particular issues, when you come for the logic, we know that we are having three different type of logic. One is your propositional logic, which is a basic one. Then we look for the first order logic and higher order logic. These are basically predicate logic. We define predicates and we try to reason about these particular predicates. So, in propositional logic, you see that these are basically or we are dealing with the declarative statements and we are going to check whether something can be derived from some other given declarative statements or not. Okay. So, like that we go for first order logic, these are predicate logic, then we go for the higher order logic. So, in this way we can go up for higher order logic, and we will see now what can be done with propositional logic, or when we need to go for the higher order logic, and what are the difficulties we are going to face if you go for the higher order logic. Since if you look into this particular order, that first I am saying that propositional, then first order, then higher order. So, that means we are going for basic logic to more and more complex logic. When we are going for a complex logic, basically what we can say, simply I can say that we are having more expressive power. Basically what we cannot express in our propositional logic, something can be expressed in our first order logic. Secondly, again if something cannot be expressed in first order logic, that thing can be expressed in the higher order logic. So, the expressive power is more. Since we are having more expressive power, so logic becomes more complex, and reasoning on this logic again become more complex. So, if we need going for more expressive power, then we have to go for a complex logic, and our that design, that logical inference will be a complex one. So, first one is propositional logic. What we can do, just simply I am just going to give you an idea that what can be captured in propositional logic and what we can do. Just these are some introductory things that I am going to tell you, and after that we will go for how we are going to do the verification. So, in propositional logic we are going for a deductive verification. What we have over here, you just see that consisting of Boolean formulas comprising Boolean variables and connectives such as and, or, etc. So, we are going to work with Boolean formulas, and Boolean formulas will be constructed with the help of Boolean variables and with connectives. All we know that these are WFF in propositional logic, which is basically a well formed formula. So, we have to, there are rules to construct well formed formula, and we are going to work with this particular WFF. And you know that whatever, if we are going to look for a digital device or digital circuit, it can be always expressed with the help of Boolean formulas. So, it is a set of Boolean formulas which is going to give the behaviors of our system. So, these Boolean formulas can be again treated as our statements in our propositional logic. So, that is why I am saying that gate level logic network can be described with the help of these Boolean formulas or propositional logic. And in typical in case of your deductive verification, what basically we check whether two models are equivalent or not, we call these are tautology checker, because in our design phase we are having an abstraction. First we come up with a model, then we will make it more refined, we will go for another level. Now, every time we have to check whether we are going to get an equivalent translation or not. So, we can look for such type of equivalent checker. So, these are basically sometimes you can say tautology checkers is also there or equivalent checker. Again we said that since propositional logic is decidable, now we have to see what is the mathematical theory about it. Since it is decidable, so we can say that it is decidable whether two representations are equivalent or not. Again tautology checker can be frequently cope up with a design which are too large to allow simulation based exhaustive simulation. So, we have problem with the exhaustive simulation. So, now tautology checker can cope up with those particular problem that we faced in a exhaustive simulation. So, in a nutshell, just I am saying that what we can do. So, basically digital system or VLSI system can be treated as a combination of your Boolean formulas, and these Boolean formulas can be mapped to the propositional logic statements, and we can use the formalism propositional logic to reason about those particular formulas. So, this is one way, but we know that the expressive power is less. So, whatever we can do, that is also restricted. The next level we are going to talk about first order logic or first order predicate logic. We know that this is basically what happens. We are going to use two quantifier, basically these are there exist and for all, and with this particular quantifier we try to capture a set of statements. Whether for all x something is true or there exists an x something is true or not. So, with the help of this thing, that means it is having slightly more expressive power. Secondly, we are having one issue, since FOL is undecidable, we have said in general. So, there may be case of doubt. So, when you use first order logic for your reasoning about system, after doing it we may have some doubt in some cases, because it is undecidable. For that manual intervention is required, and in this case some automation for verifying FOL models is feasible, but always not true. So, automation is not that possible for all cases, but sometime we may get automation also. That means, your manual intervention is always required when you go for first order logic or higher order logic. So, next is higher order logic. Again I said that this is more expressive, and so that logic is becoming more complex. So, in that particular case, what advantage we are getting? What is the expressiveness we are getting? It says that it allows function, now function to be manipulated like other object. So, that function can be treated as an object, that thing cannot be captured in your first order logic, but higher order logic we can capture it. That means, now it becomes more expressive. So, expressive power is more. So, that means, now we can express many more things with higher order logic, but since it is complex, no, reasoning with higher order logic is also complex. So, for higher order logic, proofs can hardly even be automated, and typically must be done manually with some proof support. So, this is the findings that we have. So, it is hardly can be automated, because now it is a complex, automation is not possible, but partial automation may be possible. So, we can say that interactive theorem provers require a human user to give hints to the system. Now, we are having interactive theorem provers. Interactive way, we are going to check from one sentence to the another sentence, or one statement to the another statement. For some step, it may go in an automated way. That means, we are having some formal way of doing it, but after that human interaction is required. That means, we have to give some input, so that my proofs directs to the correct direction. So, that is why we are saying that we have to human user must give some hints. That means, we have to give some inputs to go into the proper direction when we look for that reason with this particular higher order logic. So, this is basically that you know about these things, propositional logic, you know first order predicate logic, you know second order predicate logic, and second order predicate logic onwards we said these are higher order logic. Just simply I am telling you what we can capture with this particular logic. And in formal verification, when we are going to apply those things, what we are going to use in this particular lecture, I am going to tell about it, and what we will be needing for that. We need some more things, but that will be based on these three logics only. That is why I have mentioned about these three logic. So, here we need one more information. This is about time. So, you know that we are working with our digital signals, and we are going to have a controller to work with our digital signals, and we know that this system is going to behave different way at different point of time. That means, timing will come into picture. So, in our example, you think about that washing machine. Say you have started a machine, initially it has to pour the water, after that it should give you the detergent, then it will go into the wash mode. So, after some time, say around, say you can say the time like 10 minutes or 15 minutes depending on the wash type, what happens? We have to drain out the water. So, you just see that after some times we have to drain out the water, I can put fresh water into this particular washing machine. Just see, invariably that timing is coming into picture. So, somehow we have to capture this particular timing issues. We need some formalism, we need some mechanism to specify those particular timing issues. So, for that we cannot do with this particular basic logics like propositional logic or predicate logic. For that we have to go for some other logic, and this is basically temporal logics that we are going to talk about it. So, this is temporal logics, and the method, verification method that we are going to discuss in this lecture based on this particular temporal logic. So, what is this temporal logic? Already I have mentioned that I can say that it extends the notion to time actually. So, we can capture the time, and we can capture the future behavior. Now, you just see that what is a system? Already I have talked that somehow I have to capture the design issues, we have come up with a model. In most of the cases, we are going to get a finite model only. If you say slightly remove that timing issues, because in case of timing issues, it may be turned up to be a reactive system, which will repeat the same thing for several times. So, in general, you can say that we are going to work with our signals, we are having a fixed number of system, and most of the cases we are going to get finite state machine. So, the state space is always finite, and what will be the state space? If we know that if I am working with n variables or n control signals, then we know that the number of different combination that we are going to get is your 2 to the power n. That means, whatever big may be your n, always we are going to get a finite states, and every states are going to talk about some configuration, that signals values either 0 or 1, we are going to talk about digital system. So, that is why I can think about such type of your model. So, we can say that initially my system is here, say this is my, I am say that this is the state S 0, then depending on my input behavior or depending on my input signal or the system behavior, it can go in 3 different way. So, I can say this depending on some condition, either I am coming to this particular state or we are going to this particular state. If I am coming over here, that means my execution will follow this particular path. So, this is the way we can capture our design. And here you just see that this state I am in a particular time. Now, here the time is different. Again you just see that here I am going back to this particular state. So, this is the execution trace and going back to this. Now, say this particular state, basically this is this side or this is going to give the binary encoding of my this particular n input symbol, because this state I am going to define with this particular signals only. Either this signal is high or signal is low. Basically, if I am having signal, either signal may be high or low. So, this may be one particular pattern, say if I am going to have 6 signals. Okay. So, if I am going to say that this is a state where the pattern of my signals is this one. Now, say I am going to follow this particular path, and when I am reaching this particular state, depending on my situation, I am going back to this particular configuration. Here again this my input or signal pattern is same, that is why I am coming to same behavior, but when you look into the timing issues, then what will happen? When you first encounter this particular issue state, at that time that is a time is say T I. After these 3 states, say if consider that every state is having 1 unit. So, 1, 2, 3. Next time when I have gone back to this particular state, that my time is your T I plus 3. Now, this time is different, and in our case what will happen? Our issue is to get this particular timing notion, and we can do these things with the help of this temporal logic. So, that is why I am going to just give you a brief idea about the temporal logic, and this is about this module is basically talk about the temporal logic, and we are going to have a series of lecture, and I am going to give the idea about this particular temporal logic. So, what basically we are having? So, I have said that we are having 2 timing behavior, we are going to capture, we are going to use temporal logic. For that we are having 2 way of doing it. One, we are going to talk about the branching nature of time, and second one is your linear nature of time. So, in case of your branching nature, then what happens? Basically, you say that we just think that time progress in one direction only, but in case of your branching, so this is linear nature, sorry I talked. So, in linear case the time is progress in one direction only, but in case of a branching, time can branch out in several direction. Okay. Now, just come back to this particular model. So, if I am going to look for this thing, from this particular state, I can go into 3 different direction. Okay. So, depending on my input pattern or depending on my system configuration, it can follow one of these 3 particular path. So, that means I can say that the nature of timing having a branching nature at that particular point. So, it branches out in 3 different steps. But if you concentrate on a particular part over here and just say that we are interested for this particular execution part, then we may not look for other issues. So, in that particular case, we said that this is the linear time, and we are going to capture it by this particular linear notion. So, this is basically about timing issues. One is your linear and your branching, and in case of branching, when we are going to talk going to reason about this particular system, then we think about the non-deterministic issues of this particular branch timing. We can think any one of these 3 possible combination. Again, we are having another issues which is called time. How you are going to capture the time? One is your discrete in nature, and second one is your continuous time. So, basically when we talk about our digital system, we basically worked in a discrete domain. So, time can be captured in a discrete wise, and we can use the natural number system to give our time. So, I can say that the tick 1, 2, 3, 4, 5 like that. In discrete way, I can define our time, and we can say that this is discrete in nature. And in case of continuous timing, we are going to work with a real number system, where every timing instance is possible and we may try to reason about every timing instance. No, but just I am saying that either we can use the discrete time or we can use the continuous time. You know about the properties of real numbers and you know about the integer or natural numbers. From there itself, I think you can visualize that reasoning about the continuous time will be a complex one. Yes, indeed, it is really a complex issue, but reasoning about discrete system is slightly easier. Okay. So, but some system we need to reason with your real number also or continuous time domain also. Another issue we are having when we are going to capture timing, another issue we have is about qualitative reasoning and quantitative reasoning, or capturing the time qualitative way and quantitative way. So, in case of qualitative way, we just talk about the behavior of the time. We say that whether something is happening now or something is going to happen in future. Okay, just say that I am talking about that particular issue about that network protocol. When sender send a message, eventually it should get back the acknowledgement. I am talking about eventually it should get back the acknowledgement. That means, in future sender is expecting the acknowledgement. Okay, so this is some sort of qualitative timing behavior. Just I am saying that I send a message now, in future I should get it. But in case of quantitative reasoning, we specify the quantum of time also. In quantitative reasoning, what we say that now if sender sends a message now, whether after 5 units of time senders will get back the acknowledgement. So, this is a quantitative. We have quantified the future behavior, say that after 5 units of time whether sender will get the acknowledgement or not. So, these are the issues that we have to look into it. So, in temporal logic we are going to look for those issues. Now, we are going to look for, already I have mentioned that in this particular lecture we are going to look for a particular mechanism, formal mechanism to verify our system, and we are going to look for this particular model checking approach. Okay. So, now just I am going to talk about this particular model checking. So, what is the required thing in our model checking? So, we are having basically 3 components. One is your modeling, one is your specification, and third one is your verification method. That means, we need some formalism to give the model of the system. Okay. So, we have to give the model of the system, then we have to somehow specify the property, and we need a method to check whether these properties are true or valid in this system or not. So, basically in model checking we are having these 3 components. Since we are going to look for the validity of the properties or specification, it is also termed as your property verification. We are going to verify the properties of our system. So, it is a property verification. So, basically we are having these 3 components in our model checking. Now, you just see that what we are going to do with this model checking. So, what are the basic components of our model checking? So, we are having a verification tool. So, this is our model checking tool, and we are having 2 different inputs to this particular model checking tool. One is your model and second one is your specification. And I am talking about this model as your finite states, because already I have mentioned that generally we are going to get a finite number of states of our design, because it depends on the number of variables that we have. If we are having n number of variables, the total possible combination is 2 to the power n, and we are going to get 2 to the power n different states. Now, when you talk about the time, now present instance I am in a state, but in future I can come back to that particular state again, but still excluding that particular time we are having the fixed number of states, but with time what happens, we can say that now we are having more number of times, but again we are going to represent this whole system with the help of this finite state model. And this is basically going back issues is going to say this is the another time instance. Now, this is the model of our system. Say we are going to design some controller or we are going to design some circuit. First of all, we have to capture this design with the help of this model, some models. We will see in what way we are going to capture it. After that, secondly, what will happen? I have already told that model checking is nothing but the property verification. Somehow we have to specify our property or we have to give the property. So, this is the some in Greek notation we have written something and we have said that this is the specification we have given to it. Now, in both this component will be given as an input to my verification tools, and after that now this verification tool is going to check whether the given specification is true in this model or not. So, what is the output of this particular model of tool, verification tool or the model checker? If this property is indeed true in this model, then it will just give you the output OK, or it will say that the true. That means, the given specification is true in my model. But if it is not true, just say that we have come up with a design and we are trying to check whether this particular specification is true or not. So, the verification tool try to check all possible combination and it finds that this specification is not true over here. So, that my verification tool will simply, it will not simply say that it is false. Along with that, it will give me some information. This is basically, it will give me this particular error trace. So, in this particular error trace, what happens? It gives me the error trace in such a way that it says that if you follow this particular path, then the given property is not true. That means, the design team is getting some feedback from this particular verification method. Now, they can concentrate the design issues for those particular execution trace only. So, basically it may happen that others are correct. So, our bugs are concentrated over here. So, some sort of focusing the bug and design team can now look into the issues related to the things, but it does not overrule that error are not present in the other section. It may present other places also, because when designer is going to fix this particular bug, then next time it may say that error may is in some other part also. But anyway, with this particular model checking application, by applying it repeatedly, eventually we can capture most of the error and we can fix it. So, it is somehow giving the, not only saying that it is false, but along with that it gives some indication also where the possible error is. So, now where from we are going to get this particular state based machine? I am saying that we need a model. So, in the previous slide I said that these are the two inputs, one is your specification, second one is your model. Where from we are going to get this particular model? So, you just say that we are looking for this particular model. So, different people are designing the system in different way, either it may be hardware or it may be software also, and already I have mentioned that since I am going to talk about one method, verification method, it can be applied for all design cases, it may be hardware or software. So, in case of hardware, so generally what happens? We describe our system in RTL level with the help of some HDL language, hardware description language like Verilog or VHDL. So, we can have those particular Verilog and VHDL. If it is a software, then we can have C, C++ and like that, or some other design can be done with the help of that state chart, which is defined by your Herald, CSP, CSS. So, these are different way we are having a presentation, but from that we can capture our state based machine. Okay. So, we need to have formalism to get it, eventually we should get this particular state based machine for our model checkup. After that, this is the things. Now, we have to look for the specification, how we are going to give it. So, this is basically we are going to use temporal logic to specify our property. The symbol, box, diamonds are having their own notation, own meaning. In this particular module of temporal logic, we are going to basically talk about or going to discuss about this particular notation, what those particular notation means and what we can specify. So, basically now in this case what happens, you see that what we have seen that we are going to apply for a particular verification technique, which is your model checking. It needs two components, one is your model and one is your specification. We will going to look into it how we are going to give the model and how we are going to give the specification. So, next class we are going to discuss about the temporal logic, and it is going to say about the what is the syntax and semantics of temporal logic and what we can specify, what is the expressive power of temporal logic. Okay. So, next class we are going to look into this issue. So, after going through this particular lecture, you just see that some simple problems that you can think about, simple question. That first question that I am putting it like that, what are the problems with simulation based validation method? Already I have given you some idea about what happens in simulation, what happens is your exhaustive simulation and non-exhaustive simulation, why cannot go for the exhaustive simulation always. So, these are something like that you can get some more information in your book or in net, just see that what are things why it is not feasible at present. Due to the advancement of your technology also it is not feasible, because in a small silicon space you can put more and more devices. Second, this problem already I have mentioned in my lecture also, why formal methods did not get acceptance in industry earlier, because it cannot be automated. Secondly, human intervention is required, that means we need people from that particular domain, from automated theorem proving domain, because you have to guide the theorem prover while doing these things. So, that is why they were slightly reluctant and they tried with your simulation based method, but Pentium bug has forced the people to go for this particular formal methods. Third question, just I am saying that what are the advantages of using formal methods for design verification? I have not mentioned probably, but in the due course we are going to talk about it, but you just think or you just try to explore the information in net and like that. One basic thing is that we are going to use formal mechanism to specify our system or to model our system. We use some formal mechanism to give the property. The formalism that we are going to use are having a predefined syntax and predefined semantics. So, ambiguity will be removed. When it will pass to the design team, say from design team it is going to the next verification team, or it will go to the implementation team, then it will remove the ambiguity. Basically, formally we are defining it. So, all are having predefined syntax and semantics. Why it is difficult to use HOL in verification? Already I have mentioned, you can look into it and some your HOL verification methods, and you can find some more idea. Try to find out major system design failure like Pentium bugs. So, it is Pentium is not only the bug that has been reported after going into the public, some other issues are also there, some other devices are also there which has reported bug after its design or after it is going to public. You will get some information and try to compile this particular information and make a report and see what are the failures that we have due to the design error and what problems that human being are facing due to those particular errors. So, that problem 5 you can think about like that, you are going to write a report about it and try to collect those particular information. We are having several design error fault in our history. So, with this I am winding up my lecture today. So, next class we are going to talk about, or we are going to discuss about the temporal logic, about its syntax and semantic. Bye bye.